Hi again. Hope you are staying at home very safe without being affected directly from the issue virus spread. So today we will actually, like, we've been talking about the DC circuit analysis, and we have come to an end in the last lecture. So from now onwards we'll be talking about the AC analysis. So to start with, we will be today spending time, or in this lecture we will be spending time to learn about the some basics on AC circuits, some components that you might not have seen in the DC circuits, and then basic stuff behind AC circuits. So the title is AC Fundamentals. The reference chapters are 10, 11, 13, 15 and 16 of the reference book. So to start with, we look at capacitors and inductors. These are, well, actually we talked about these capacitors earlier, but we did not use them in the applications or circuit analysis problems. So earlier when we talk about DC analysis, we didn't have capacitors and inductors, we had only resistors there. But now in AC analysis we will be getting capacitors and inductors. So capacitors can be used to store a little charge in them. Let's say it is Q, and Q is equal to C into V. That is a basic equation that we will have to remember, or we will have to use. This equation, of course, we have talked about earlier. C is equal to, that is the capacitance, is equal to epsilon A over D, where epsilon is the dielectric constant, and A is the cross-sectional area, and D is the space between plates. So in this case, Q is equal to CV, that is Q is the charge stored in the capacitor, which is equal to the capacitance times the voltage across the capacitor. Now the total capacitance of a parallel combination, for that actually we can use the equation, the relationship that we just discussed, that is QV is equal to CV. So if we assume that the charge of this capacitor C1 is Q1 and C2 is Q2, the total charge in here is Q. So the charge in here should be the charge, total charge in here. So in that case it's the same voltage, so therefore we had to have, if it is equivalent, then we had to have both the sides equal. So from that you can get Q is equal to Q1 plus Q2, using QV is equal to CV. From left hand side you get CTV equals to C1V plus C2V. The voltage is same for both the cases, so voltage can be cancelled out. This will, so therefore they are reduced as CT equals C1 plus C2. So that's this relationship. We can extend that into any number of parallel capacitors, C1, C2, C3, any number. So that's the parallel capacitors. When it comes to series capacitors, again we can use the same technology or same approach, but here it is if it is plus Q, this side minus Q, so plus Q minus Q, plus Q and minus Q. So it's the same capacitance, that same charge that you get in all these capacitors. So however we can write for the voltage, V is equal to in here again, in that case, this end you have plus q, this end you have minus q, so it is actually a q charge that you have in the equivalent capacitance as well. All the capacitors also, each capacitor we will have a charge of q. So from voltage, V is equal to V1 plus V2. Let's write for only two capacitors. Or even if you extend that to Vn, there is no harm in there. Now Q is equal to CV, right? So Q is equal to CV. So V is equal to Q over C. So here we will have Q over CT. In these capacitors, it is Q1 over C1 plus, sorry, it's again Q. Q over C1. Let's take the eraser. And Q over C2 plus up to Q over Cn. So Q cancels out, which will give us 1 over Ct equals 1 over C1 plus 1 over C2 plus up to 1 over Cn. Right, so that is what you get. Actually, if you look at these two equations, this is just like the parallel series resistors, although it is parallel capacitors. It's the addition. This equation looks like that for the parallel resistors, but in this case they are parallel series capacitors. Now we can use the series set of capacitors to get a voltage divider worked out. So using again Q is equal to CV, for one capacitor Q is equal to C1V1, and for the total set Q is equal to CTV T, the total in this case the total voltage Vt, right? That is this voltage Vt. So if you divide one by the other, or these can be equal to each other, so therefore V1 C1 or V1 C1 is equal to Vt Ct. So from that you can get V1 is equal to Ct over C1 Vt. Now previously we had this resistor voltage divider, where when we wanted to find V1, what we had on the top was R1, and what you had on the bottom was the other resistance. But in here what you have is what you had in here is the total resistance, but in this case when it comes to voltage divider, then what you get is capacitor voltage divider. You get the total capacitance at on the top, and particular capacitor across which we are taking V1 or V out at the bottom, right, at the denominator. Right, okay, so that is the voltage capacitor divider. In most cases we are using them for AC applications, but not for DC applications. Right, so the charging the relationship, the voltage current relationship is given by this equation. Will come there. Now Q is equal to CV, right, and I is equal to actually dQ by dt, the rate of change of charge, or rather charge transfer, is the current. So charge transfer rate, that is dq by dt, is actually our IC, which means q has to be derived by the t in here. C is a constant, so therefore we can take it out. So in that case IC becomes C dVc over dt. So that is the time domain relationship between the current and the voltage of the capacitor. Now in the case of the resistor, it was V is equal to IR, or I is equal to V over R, which was the Ohm's law relationship. It was linear. But here you can see that it is not a linear, but it is related with the first derivative of the voltage. The current is the first derivative proportional to the first derivative of the voltage. Now if you have a capacitor connected to a charge or voltage source like this, the voltage variation looks like this. That is, I think, the same. Okay. Yeah, so same thing that is discussed in here, right? So from this equation we can see that, okay, if you apply KVL to this loop, E is equal to VR plus VC from here. So VR is I into R. IC, the capacitor current, is actually the current going through the entire circuit in here. So VR, the voltage of the resistor, is equal to IR. So I is IC to R. And for the capacitor, IC is related to the capacitance in with this equation. So if you okay, so in that case VR is also equal to R into C dV by dt. Now when we take this into we substitute with VR in this equation, you get this equation where RC dVc over dt plus Vc is equal to V. Now we have a differential equation. The solution for that is Vc is equal to E into 1 minus e to the power minus t over RC. At this point you don't have to worry much about how you came from here to here, but it is using the differential. We have a first order differential equation. From that you can get this equation. Now in that case VR is equal to E minus Vc, so you get VR equal to E into e to the power this, right? E minus, so you get this cancelled out, and IC is equal to that value divided by R, right? So from this relationship. Now if you take this, we call this RC as the time constant tau. So tau is equal to RC. So at t is equal to 5 times tau, or 5 times the time constant, or 5 times RC. What about Vc value, right? Then Vc is equal to E 1 minus e to the power minus 5, right? What is this value? E to the power minus 5. Let me check with the calculator. Okay, e to the power, where is this? Okay, let me bring the scientific calculator. Oh, you got the scientific calculator here, right? Okay. That's it. That was e to the power minus 5, right? Yeah. So minus 5 e to the power is this. So 1 minus that is that this this minus 1. So it's 0.9932. Or this will be actually now equal to this is equal to 0.99 E, which is very close to E. So in practical scenarios, this is actually less than 1% error now. So in practical conditions, we assume that at 5 times time constant, the voltage of the capacitor goes to its full voltage. So that is what practically we consider. During the discharge, the circuit actually, if it is a charged capacitor charged to some voltage, let's assume that it is E, and if you discharge it, the relationship will be the same thing that we have here, that is the voltage drop of this plus Vc equal to 0. So this will give us Vc equal to V naught, that is the initial voltage. In this case it is E, e to the power minus t over Rc. So it is the discharge curve that you have now, and in this case again, at 5 times time constant, we assume that the capacitor is fully discharged, right? Likewise, like in this case it is 99% discharged. This case it is 99% charged, but in the discharge case it will be 99% discharge, right? So this actually sums up everything, the charging of the capacitor, right? Time constant and those stuff, right? It's okay. And for inductors, V is equal to LdI by dt. That is actually from the laws, scientific laws that you have there. One more thing I think I have forgot to mention in here, where is that? Q is equals the energy stored in the capacitor is half CV squared for the capacitor, and for the inductor it is half Li squared. And the relationship is now, in the case of the capacitor, it was V C is equal to I is equal to C dV by dt, but now it is the other way around. V is equal to LdI by dt. This equation we discussed, which is not very important at this stage. If you are winding an inductor, the inductance would be given by this equation. Mu is the magnetic constant of the medium, and then n squared is the number, n is the number of turns, L is the length, A is the cross-sectional area. Now when it comes to inductors in series and parallel, they are alike. They follow the equation of the resistor. So for series resistors, it is series inductors, it is the sum of the inductance, the total inductance. For parallel, it is 1 over the total inductance is the sum of reciprocal, so 1 over L1 plus 1 over L2 and so on and so forth. So this is as same as that of the resistors. So L is the inductance is what we talk about in here. Now the difference between this is the main introduction to the AC, that is alternating current. Although we have the word current in there, we are not referring to the current itself, both voltage as well as current. Here the word alternating current implies that the both voltage as well as current is alternating. Now if you could recall, the DC, the output of a battery, was pretty constant, right? It's a static value, DC value. However, when it comes to AC, well, these amplitudes are constant, but the variation is always there. So that is in Sri Lanka, the frequency is 50 Hz. I'll talk about frequency a little later on. Frequency 50 Hz means 50 times it goes to positive and negative continuously. So it's not a constant voltage as such that you see, both for voltage as well as current. We will look at what is the behavior between the voltage and the current little later on for different devices. Like we talk about 3 devices now, the resistors, capacitors and inductors. So we will look at the variation of the voltage and the variation of the current with the AC. However, the main difference is that this is steady and this is actually fluctuating between positive and negative. Alternating means it has alternating polarities, so it has positive as well as negative continuously. Yeah. So during the positive half cycle, the actual current, although we mark it in any direction in the circuit, let's come into that little later on. The actual current will flow in this direction from positive, because this side is positive half cycle. Negative half cycle, this side is positive, this side is negative, so the current would go in the reverse direction. So likewise, current will flow, voltage will be this way, current will be this way. This is for resistor, right? We will talk about little later on for the capacitor and the inductor. Now what is the reason behind this variation of the voltage is the construction of the generator, right? So I'm not going to talk about much of details in this. At this point the current will be actually 0, the voltage will be 0. At this point, let's say if it is at positive peak, again it will come to 0, and again it goes to negative peak. So that is the behavior of a AC generator. We will be talking about AC generators in the second year for electrical students, but for the moment we just want to see. I think this was discussed in the science in, I think, grade 9, 10, somewhere there. So just want to know the phenomena behind this generation. So this is why it is having both positive and negative voltages, and it's going on a sinusoidal direction, sinusoidal shape. The sign convention of AC, right now we will be still marking the direction of the currents as well as the direction of the voltage. That means that all current, now this is time varying, as we discussed in the previous slides. It is always varying between positive and negative. So what is meant by this is in this one is any currents that are going in this direction will be treated as positive, and current going in the reverse direction will be treated as negative half cycle, right, or negative. And for voltages, the voltage developed on that direction would be treated as positive, and reverse direction would be treated as negative. So that is the main sign convention when we are talking about the current. So now if you mark several currents in the circuit, we must know that all will be positive at a given time and everything will be negative at a given time according to directions that we have marked. Same would be for the voltages. Everything, all voltages will be positive in a given point and negative in a given point. So that is how you actually mark, keep the sign convention continued. There is another case as well, the letter representations. If you use upper cases, they are time invariant parameters. Lower cases, they are time varying parameters. So as you can see in here, the amplitude, or rather the height of this, is constant throughout. So it's a time invariant value. But the instantaneous voltage, actual voltage at a given point, is always varying. So it's a time varying parameter. So time variant parameter or time varying parameter. So for a time varying parameter, we will be using simple letters, like for voltage sources E, and voltage drops simple V, and current drops simple, or currents simple I. Time invariant parameters will be represented by capital letters, capital E for sources, V for voltage drops, and I for the currents. Let's look at, we will come across some of these parameters little later on. We will look at them when they are there. So the definitions, let's call them as definitions. So we'll identify the key features of waveforms. First one is the number of cycles per second, which is referred to as the frequency. So it's actually number of cycles per given unit time. In the SI units, it is per second. Unit time is second. So number of cycles per second is actually the frequency in hertz. Then frequency will be defined by the simple letter simple f, and the unit is hertz, right? So the person who actually defined this is Heinrich Hertz. And in this case, you can see that, okay, for a given cycle you have for 1 second you have 1 cycle, meaning that the frequency here is 1 hertz, and here you have 2 cycles per 1 second, which means that it is 2 hertz. Period is actually 1 upon frequency. This is number of cycles per second, so period will be given by 1 upon the period, 1 upon the frequency, right? So frequency can be actually, or period can be defined from any point to the next similar point, the very next similar point. So in that case, it can be from this zero crossing to this zero crossing, or even this zero crossing to this one similar points, or as you can see here, from this point to the same next point, this one, even from peak to peak, they are positive peak to peak, negative peak to peak, or at any point to the very next similar point. So that's the period. Few more parameters. Amplitude is the distance between from 0, or its mean value, to the peak amplitude. Peak to peak voltage is, as you can see here now, this is defined by a uppercase because it's a time invariant parameter. Even the peak to peak voltage is time invariant, which is actually equal to the to 2 times the peak, 2 times the amplitude. And peak value actually is defined as the value from 0 to one of its peaks. So positive peak, negative peak, it's the peak value. So usually what we are interested of in this year's study, when it comes to signals, we may be interested of all these values, but currently what we are interested is to the peak voltage, the amplitude, and the peak to peak value. Sometimes we may be defining peak to peak value, sometimes we may be having just a amplitude, because most of the practical scenarios, the AC voltage will be a sinusoidal voltage that's average is at 0, right? So there is no shift like what you can see in here. So it's something like this what you have. So in that case we will be interested of the amplitude and the peak to peak voltage, right? So the peak value here, the peak value is actually, now this is E is the shift, DC shift, we call it as DC shift. So E plus capital EM, that is the amplitude, is your peak value, positive peak value, and negative peak value is E minus EM. So the positive peak and the negative peak of the waveform. Effective value, now effective value is, let's assume, now this is a time varying component, this is always varying. Now because of that we want to find out an alternative which is DC. DC voltage source, if you give, if it is a voltage, if you apply that DC voltage to the same load, same resistor, it should be generating the same power, right? Now let's say you assume, you consider, you connect the AC source to the same resistor, another DC source is there which is connected to the same resistance. If the same power is generated, what we want to find is the DC voltage, DC value, DC voltage or the DC current at which the resistor generates the same power. So let's read this and see. An effective value is an equivalent DC value. It tells how many, it tells you how many volts or amps of DC that a time varying waveform is equal to in terms of its ability to produce average power. So that is what it said, like if it generates the same power with the DC, at what voltage or at what current would the load generate the same power. That is what is the effective value is. It is also called as the RMS. Let's look at later on why this RMS and what this RMS is. So okay, let's take this. I'm not going to do the derivations at this point because all these equations are given here. Now right, when it comes to power, P is equal to I squared R. We talked about that when we were talking about the power, right? V is equal to I squared R, right? Actually we talked about the power and efficiency thing. So in there we were talking about P is equal to VI, P is equal to I squared R, I squared R, and V squared over R. All these equations we talked about. So assume that this is the current. The current is what we are talking about, and I squared R is the power, instantaneous power. Now I is given by Im sine omega t. It's a sinusoidal. So when you square it, you get this equation, I squared omega t. You can simplify this I squared using one cos 2 theta equation expansion, which is 1 minus cos 2 omega t. Now the average of this is the average power. Average of a cosinusoid, a sinusoid or a cosinusoid, is 0. So therefore average, this part will go off, the average would become this one. Or else you actually integrate this over a period of over one period. This is one period is in this case actually this one. You don't have to go for the full cycle here, full cycle of the input waveform or full cycle of the current source, but this is actually a cycle for the current source or the power. You do that integration over a period, and that's actually because this is 2 sine omega t, sine cos 2 omega t, so that is twice the frequency, right? Anyway, if you do the integration or whatever it is method, you can find out the average in here, which is equal to Im squared, that is the amplitude squared, or the amplitude of the current waveform squared, R into R over 2. Now if you on the other side, if you assume that okay, there is a DC source that is connected to the resistor, which allows the resistor to dissipate the same average power, in this case it is I squared R, right? So I squared R is equal to I m squared R over 2. So when you equate these two, you get I squared is equal to I squared m over 2, meaning that I is equal to I m over root 2. So that is the effective value, right? So effective value for a sinusoid is the amplitude divided by root 2. So we can use that for currents, voltages, EMF sources, so that is for the source voltages, or for voltage drops, anything, or reverse direction of that is the amplitude is equal to root 2 times the effective value, right? Now effective value in this case, okay, look at this. I was talking about that integration part, or using integration for averaging. Now this is a current, right? Power should be integrated over a period of time, right? So it is actually what is integrated is the square and average, and we'll have to square root as well, of course, because we are doing the square root in here. So in that case, square is integrated over a period, actually averaged over a period, and then taken the square root. Right? So this actually gives you the effective value, because that is the same procedure that we actually followed so far, with different techniques, of course. So now you can see why it is called as root mean square. Root of the mean of the square is what is this, what will this value be. So RMS, root mean square. Now this is why we actually use the term RMS for the effective value. So in that case, we RMS is equal to the peak or amplitude over root 2. On the other hand, the opposite direction of that is the amplitude is equal to root 2 times the RMS, root mean square. Now representation of sine waves. Now I am doing at a stretch, don't worry about it. You can always pause the video, right, and spend more time, rewind it, replay it, and all that stuff can be done, right? And up until the point that you actually understand that, you can actually review the video again and again. Anyway, if you have any doubts, you can post that to the WhatsApp group, and also you can table those concerns or doubts in the discussions that we start from this Friday, that is tomorrow actually. Right, so sinusoidal waveforms can be represented using rotating vector, or mathematically using this equation, which actually we used earlier as well. So Em sine alpha or sine omega t. Omega is the angular frequency, t is the time. When it comes to the measurements, radiance measurements, 2 pi radians is equal to 360 degrees. So that equation can be used to convert between radians and degrees and radians. But your calculators got all these features. Have a look at your manual of the calculator to find out how you convert from a radian value to a degree value, and degree value to a radian value. Now from this equation, it is 2 pi radians is equal to 360 degrees. So pi radians is equal to 180, right? So that is the relationship that is used in here, right? Whatever the angle in degrees is equivalent to 180, so that has to be divided by 180 and multiplied by pi, or divided by 360 and multiplied by 2 pi. So whatever it is, other way around is also working. So if you mark it on an x-axis in a waveform, so this is using the angle decrease, angle radians. Also you can use the time, that is periodic time. This is full 1t, half a t, 1/4 of a t, 3/4 of a t. So with that, the relationship between omega t and frequency is omega t is equal to t. For now, omega is the angular velocity, that is the angle covered per unit time. So if you multiply that by the time for the period, that is equal to 2 pi radians. So this will give you that omega is equal to 2 pi over t, or omega is equal 1 over t is f, so therefore 2 pi f, omega is equal to 2 pi f, angular velocity is equal to 2 pi f, or frequency, natural frequency is equal to omega over 2 pi. We'll write that as well in here. So f is equal to omega over 2 pi, right? So in that case we can write the three equations. Just for completion, I have added most of these slides. E simply can be written as Em sin omega t, V can be written as Vm sin omega t, I as Im sin omega t. So that is mathematical representation of EMF sources, voltages. Now when we are talking about multiple sources, now if you have only one source, we can always treat the starting point always the voltage starts at the zero crossing, right? But when we have only one source, but when you have multiple sources, there can be in time one source, when one source passes the zero crossing, another source may be somewhere here, one may be somewhere here, or somewhere here at a different point. So to represent that, you need to have a phase shift. So phase shift is, if you can actually, like, let's say in this one, let's say when there was a source that was starting at 0, but this was before that, it was crossing 0, so therefore that angle is plus t. This is referred to as the phase shift. This has a positive phase shift, and it is lagging or delayed, that will be minus t, or omega t minus t. So that is little late than the zero crossing point or the other waveform. So that has a negative phase shift. We call this as having negative phase shift, and this as having positive phase shift. Just the principles, right, for you to understand. So this actually is important. Whenever you have only one source, we can actually start timing at the zero crossing. There is no issue in there. But when you have multiple sources, when one is at the zero crossing, another we may be little earlier, another may be little late. So based on that, we had to use the phase shift to represent when there are more than one source in the circuit. Now, if you think of this rod, right, rotating around, or this is called as a phasor rotating around the axis, right, the projection on the vertical direction is Vm sin omega t. So that does mean that a rotating phasor, if you look from this side, can be used as a used to represent a sinusoidal waveform. Now let's take this as an example, right? So this is a rotating phasor, and you can see that this waveform varies in a sinusoidal manner. If we have multiple sources, right, you can still represent that. Now I'll actually pause it. Well, pausing means I have to exit from this. Keep it. Now if I pause it, you can see the relevant positions of the three waveforms. So you can take any actually, right? You can consider at any different point, but if you just pause it, right, take a screenshot, that represents the relative positions of the three phases of this rotating set of phases. Now, okay, we'll come into that little later. I just give you a hint like that. If you just pause at this one point, that is referred to as a phasor diagram. We'll come into phasor diagrams little later on, but for the moment you can see that a set of rotating phasors can be used to represent a set of sinusoidal waveforms. So in variable or time varying format, it is the rotating phasor, but if you take a snapshot of this one like what you did in here, this can also be used to represent these three sets of waveforms. Given that this is all these phasors are rotating at the same rate around this same point, right? Okay. Now the phase difference between the voltage and the current, if the voltage and the current overlaps or exactly synchronizes each other, it is referred to as in phase. If current is actually having a positive phase shift, meaning that it is happening little earlier with the same frequency, both these have same frequency, but this is little prior, this occurs little prior to the voltage waveform. In that case, voltage is lagging, current is leading. So let's write that part as well. Current leads, voltage lags. Now in this case, current lags because as you can see here, current is little delayed from the voltage, so it is lagging behind. That is what means what is meant by lags. So current lags, meaning that voltage is leading. Voltage leads. Right? Now that is actually lagging and leading, all is dependent on now we can consider that when you look at a point, whatever comes first is actually the leading waveform, right? It crosses earlier, this is rotating in this direction, this is crossing you at an earlier stage, then only this comes, so which means that IM is leading and VM is lagging. Now in the phasor diagram, you can see that in this way, you can see if you have a positive angle from here, that is actually a leading waveform, this is lagging. So it can be at different positions. We will look at that little later on. Now we have talked about three different components: a resistor, a capacitor, and an inductor. Now we will take one by one and see how, or the interrelationship or the phase relationship between the voltage and the current. Now if let's assume we are we are going to take in this case voltage as the reference. Let's say if I is equal to V over R, if we take V is equal to Vm sin omega t, this is the sinusoidal representation, we get IR as Vm over R sin omega t. So Vm over R can be defined as Im, which is the amplitude of the current source. So in that case, as you can see here, the angle between these two is actually 0. So this is at 0, this is at 0, so the voltage and the current will be on the same direction, meaning that they are in phase, right? So let's in phase, right? So if you draw it, it will look like this, right? And this is for the Im, this is what I talked about. Vm over R is given as Im, defined as Im, so Vm is Im into R. So V is equal to IR relationship holds in their in the magnitude values as well. So if it is held for magnitude, it will be held for RMS as well, because RMS is magnitude over root 2. So if you divide both these by root 2, this doesn't do any change to the equation of the relationship. When it comes to a capacitor, or rather inductor, we know that VL is equal to LdI by dt. So if we take I as Im sine omega t, you take the derivative Im sine omega t into omega. So omega L Im, if we define this as Vm, all these are constant. Omega is a constant, L is a constant, Im is a constant. Im is the amplitude. Amplitude doesn't change time to time, right? In very special case that may, but in usual cases that we are talking about, Im is a constant. So Im, Il, Vl, all omega L and Im, all these parameters are constant. So we can define this product to be equal to Vm. So Vm cos omega t, and well, cos omega t can be written as omega t plus 90 degrees. So that does mean that voltage is leading by 90 degrees, right? So if you if you draw it in a sinusoidal waveform, it's look like this. Even you can rotate it as well. So if you draw the current as reference, that is what we did in here, current taken as reference, you actually have to draw the voltage as vertical, because it is leading by 90 degrees, right? So there is a right angle, and if you actually rotate this whole thing towards that side, you get this. So if you take voltage as reference, current is lagging by 90 degrees. Both these are correct. Even if you put it like this, voltage and current still have 90 degrees phase shift between them. This is also correct, right? So the main requirement is that these need to be spaced at 90 degrees, while I is lagging, V is leading, right? So the relationship between inductance and inductive reactance, XL. XL is what we call what we define as Vm over Im. We have got the relationship for Vm and Im in here. So Vm over Im is omega L. So XL is omega L. So this is the relationship is V is equal to IR like. So instead of R, we put the reactance, inductive reactance XL. So V is equal to XL into I, IXL. So XL is now omega L from the earlier definition. Right, so that's that. Even if this will hold for the RMS, because Im over root 2 Vm over root 2 doesn't do any change. So this gives you the relation indication of omega or rather XL when XL changes, or rather how XL changes from frequency, right? Inductive reactance changes for frequency. Inductive reactance, or rather inductance, is a constant, but inductive reactance, as you can see here, is a frequency dependent parameter. Increasing frequencies will increase the inductive reactance. Right, so the capacitance and the behavior with capacitances. For the capacitor, we know that IC is equal to C dV by dt. So V is equal to Vm sine omega t. If we take V as reference, derive first derivative, Vm will come out, omega will also come out, because omega t will have to be derivated by d by dt. So omega will come out, so omega cvm cos omega t. And now you can see cos omega t can be again written as sin omega t plus 90. So current is leading by 90 degrees to the voltage, and this relationship also will hold. So V is equal to xc, Im xc will be 1 upon omega c. So okay, if you draw, now we took voltage as reference, so V has to be horizontal, and the angle of phase angle of I was positive 90 degrees, so that is going upwards. So this is going horizontally, and this is going vertically up. Even if you rotate it a little bit, whatever the direction that you rotate it, as I talked about earlier, voltage will be lagging by 90 degrees to the current, or current will be leading by 90 degrees to the voltage. So this way you can draw the phasor diagram at any orientation. The main requirement is that they will have to be separated by an angle of 90 degrees in a way that IC is leading and VC is lagging. So for a capacitor, current is leading, and for a voltage, for an inductor, voltage is leading. So we'll have to keep that in mind, right? So if you draw the waveforms, they will look like this, right? They will be shifted by an angle of 90 degrees. So VC is lagging, as you can see here. Okay, why is it lagging? So let's talk about this point. This is going downwards, negative gradient crossing this point, but the negative gradient crossing for the voltage will occur exactly half or 90 degrees, so half a pi after. So meaning that VC is lagging. Same for the inductor as well. Inductor, if you look at the inductor waveform, you can see that let's take this rising okay, the falling edge. For that falling edge of the voltage occurs here, exactly another half a pi. Current is falling, zero crossing is there, so current is lagging in this case, voltage is leading. But for the for the capacitor, it is other way around, voltage is lagging, current is leading. Now the relationship between xc is v over I, Vm over Im, which is 1 upon omega c. So the frequency dependency or frequency variation for the xc, the inductive reactance, higher the frequency, the lower the reactance is. So again here the inductive or rather capacitive reactance is a frequency dependent parameter, although the capacitance is not. Right, so all right, now complex numbers. Before we start complex numbers, why are we discussing about complex numbers? Now we talked about these phases, and that the sinusoidal waveforms can be represented by phases. Now this is a picture, right? So you can understand the relative positions of this. But when you want to mathematically manipulate that, you need to find some method to represent this in mathematical means. So in that case, okay, either you use vector representations, then the business becomes little difficult, because you need to have unit vector in this side, unit vector in that side, and so on and so forth. And vector calculations are of course little tedious. Or else you can use Cartesian coordinates. You need two coordinates, so x comma y to represent a vector, assuming that all vectors or all of these start at 0. It actually starts at 0, right? So you need x comma y sort of representation to represent a vector. That also, like if you want to add 2, what how are you going to add, and things like that would be a trouble. the best solution would become the complex number representation or the complex number domain, where you don't have any constant to represent the real axis, but you have the imaginary constant to represent the imaginary axis. In that case, you can add up any of the components in the imaginary direction, that is vertical direction, any component in the horizontal direction using the what is that, not vector calculus, but complex number calculation. So you can use the full spectrum of complex number calculations if you represent these in the complex number plane. Now keep in mind, okay, when it comes to complex numbers, there are imaginary components, right? But keep in mind, the voltages, currents, and everything that we are talking about are very real, right? There is no imaginarity in there. However, we use the complex number plane to represent the phasor that we use to represent the sinusoidal waveforms, maybe current, maybe voltage, whatever it is. This is just a representation, right? So it, instead of using two constants for the horizontal and vertical axis, we use the imaginary constant in this case, right, for the vertical. Now in that case, we can represent a vector in the Cartesian form or the polar form. In the Cartesian form, real value plus I. We used to use I, right? But now you can see in all electrical books, complex number, the imaginary constant is represented by a simple J. That is because simple I is already used for currents, right? Currents are represented with I1, I2, maybe whatever it is. So if you don't have many currents, if it is simple single current that you have, if you even go back in this slide set when we were talking about the capacitor charging and discharging, now in this circuit you can see that it is simple I. So if you have simple I, the current here, and the imaginary constant as simple I, you would really mess up with the calculation. So therefore they use we use simple J to represent the imaginary constant. It is nothing other than the minus square root of minus 1, right? So here J is square root of minus 1, right? Imaginary constant. Right, so nothing other than just a different label. Earlier we so far in the O levels and A levels, if you have done both, I mean at both levels, it was actually I was used to represent square root of minus 1, that is the imaginary axis, but now we are using J instead. That's all the difference is. And if you want to represent the same thing in the polar form, you use the amplitude and the angle. So this is mainly, most of the cases, this is what we may be having, but this will also be there because you may have real components, imaginary components we will see when there is 90 degrees shift, it will be in the vertical direction. Let's look at those when it comes. Right, so the combination or the conversion between, or the relationships that we have with complex numbers, C can be represented as a complex number, A plus JB, or C angle theta. Now in this case, simple A is C cos theta and B is C sin theta, given in here, and C is equal to square root of A plus A squared plus B squared, right? So square root of A squared plus B squared is B. So this is using Pythagoras law, right? And theta is equal to tan inverse B over A, right? and A into B, that is A multiplied by B. If you have two complex numbers, you can use A, B, that is the like C values, the magnitude values, and angles will be added. If you divide, it will be A divided by B, the sizes will be divided and angles will be subtracted. And reciprocal is actually 1 over C minus theta, so we will have to take this angle upside up to the top, it will be minus. Conjugate, complex conjugate is the complex conjugate of C is C star, which is A minus JB, so it is actually real component will remain unchanged, imaginary component will be in the reverse direction. That is what is complex conjugate is. Now 1 point. Okay, although we have all these relationships mentioned, your calculator will allow you to transfer between these parameters, that is Cartesian A plus JB. So the calculator will allow you to use cal to convert between A plus JB to C angle theta. So you can use the calculator, but keep in mind, when you are entering a value in the calculator, it will be actually I that you will be having in the calculator, and we have to enter as A plus 5I, something like that, not I5, right? But although in mathematical representation in electricity analysis, we will be always putting the J in front, right? Keep that also in mind. Right, now complex numbers used in AC analysis. How many slides have we spent? We'll look at later on. Right, nothing to worry. Right, so okay, ET is equal to EM sine omega t plus theta, given that there is a phase angle as well, so it can be represented as EM angle theta. So this is the phasor that represents the voltage source. So in that case, if you can use either EM angle theta or the xy coordinates of the E. Most of the cases, the voltage sources and current sources, we prefer to use the polar form, whereas when it comes to impedances, we most of the time we get rectangular coordinates, although it is not a must to get rectangular coordinates only for loads, and polar coordinates only for sources. But because why the polar coordinates is preferred to voltage sources is that when it comes to voltage sources as well as current sources, for both the sources, because we know the magnitude or the amplitude of the source and the phase angle. So these are the first hand information for a source. But maybe for an impedance, maybe for a load, but the first hand information may be the resistance value and the reactance value. Now reactance is, we talked about the capacitive reactance and inductive reactance earlier. So inductor values and capacitive values and the resistor values are what are the first hand information for a load. So in that case, they will be, we will see how you represent the reactances and the resistances. So in that case, the first hand information may be the Cartesian coordinate parameters, but for a load, a source, it is EM and the angle, the amplitude and the angle, the first hand parameters. So several examples are shown in here, nothing serious. Plus 40, so there is a positive 40 degree phase shift. It's the same thing represented as this, whatever it is, all these essentially represent the same thing in different domains. Right, now the impedance, like the resistance was V over R, but now we know that we have phase shifts and things like that. So voltage is a complex voltage is represented by a complex value, current is represented by a complex value. Now you could have observed that I started saying that voltage is a complex value when I switched my phrases, and I said voltage is represented by a complex value. This is to insist the point that it is not a complex value in reality, but we use now complex means that it has imaginary values, like non-real values, right? Imaginary means non-real values. Like what you have, I mean, you may have a lot of imaginations in your mind, but they are not real, right? So likewise, that is why I want to insist the point here that voltage is represented using a complex number, current is represented by a complex number. They both are very real, right? But they are represented because of the phase shift in the complex domain. So this value is the representation is in the complex domain, this is in the complex domain, and therefore we will have to define another parameter, which is the impedance. It is not just the amplitude what matters, an amplitude and an angle that matters. So V angle theta 1, I angle theta 2. So V over I theta 1 minus theta 2 becomes theta. So that is, if you write the voltage in the complex form, current in the complex form, divide them together, you get divide voltage by current, you get the impedance. So impedance is also represented in the complex number domain. So it has a amplitude and angle, right? So V is equal to IR. Synonym here is V is equal to IZ. Now here, as we can see, V and I are the RMS values. They are large letters, capital letters, so they are not both V and R are RMS values. Sorry, V and I, right? V and I are RMS values. They are not the time varying parameters. So V and I are RMS values. So Z then also Z is also in complex domain, right? So these are RMS values that you take here. Right. Now for a resistor, we already talked about that. V divided by I, they are interface. Right? So V is equal to V angle 0, I is equal to I angle 0. So therefore impedance is equal to R angle 0. Now when it comes to an inductor, voltage is leading. So if you say I is equal to I angle 0, V is equal to V angle 90 degrees. So V over I is V over I angle 90 degrees. So that is going upwards, meaning it is in the J direction. So the value is omega L. We already found that earlier, but now you have a J there because the angle of the reactance now, or the impedance for a pure inductor, is 90 degrees, which is going upwards. So therefore now you see that the reactance, imaginary components are involved in representing the reactances. So inductive reactance ZL is going in the positive direction of the imaginary axis, because there is this phase shift. Voltage is leading to the current. To represent that, you have this 90 degrees phase shift. Okay, now for a capacitor, we know that current is leading. So if we label V, take V as V angle 0, I will be I angle 90 degrees. So V over I is V over I angle minus 90 degrees, meaning that it goes downwards, so minus j direction. So that is why you have this minus j term in here and plus j in here. That is because when you divide the voltage and the current by the definition of impedance, you get that 90 degrees phase shift, 90 degrees phase angle for the impedance or the reactance. To represent that, you will have to actually involve plus j or minus j in the complex number domain. Again, I'm insisting the point, I'm highlighting the factor that none of these are imaginary things or unreal things, all these are real, but we use the complex numbers to represent the parameters. Impedances in series, so you add up the values. All these are complex numbers in here because, as we saw in here, in general they can have a phase shift, so they will be represented by complex numbers. So adding them is possible. Now when you add these numbers, we all know okay, so you know that let's say a plus a1 plus jb1 plus a2 plus jb2 in the complex numbers would occur earlier. We did not discuss that, I guess. Okay, anyway, a1 plus a2 plus jb1 plus b2. So it's just a matter of adding the real components together and imaginary components together. Anyway, you don't have to worry about that too much because your calculator will help you in doing this. Now an example, impedances in series. So you have a resistor and a reactance in here, inductive reactance. So a resistor is actually 3 plus j0, and this is 0 plus j4 plus j, because this is an inductance. As you saw here, it is plus j, right? So it's 3 plus 0j, 0 plus 4j, add together, so it's 3 plus 4j. In the complex numbers, you represent it like this. You have 3 ohms in this direction, 4 ohms in that direction, so the resultant is 5 with an angle of 53.13, right? Now you have another example in here, right? You have actually a capacitor and an inductor in series, right? Let's look at the effect here. So this is let's write it, right? This is 25 plus 0 j0 plus 0 minus j200 plus 0 plus j225, right? Now 25 is there, minus j200, oops, I'm sorry, this is plus and that's minus. Capacitor is minus, sorry, capacitor is minus and sorry, capacitor is minus and inductor is plus. I messed it up. So plus j200 minus j250, so it's minus j225, minus j25, meaning that the moment that you have minus here, it is capacitive. So it's not a capacitor, but it's more capacitive than more inductive. Now what if XC was j200 then we will get ZT equals 25 ohms, because 200 and 200 cancels out. So in this case it will be pure resistive, right? So also, if actually let's say if right, XC is 150, J150, then ZT will be 25 plus J50, right? So which is then inductive, right? So you can see, if inductive reactance is larger than the capacitive reactance, the total circuit will become inductive. If the capacitive reactance is larger compared with the inductive reactance, then the total circuit will become capacitive. If both capacitive reactance and inductive reactance are equal to each other, the total the effect of the capacitance, capacitive reactance, will be fully cancelled by the inductive reactance, and vice versa, and as a result the total circuit will become a pure resistive circuit. So inductive reactance is fully compensated or fully cancelled out by the capacitive reactance if both reactances are equal to each other, because one goes in the positive direction of the complex or imaginary axis, and the other goes in the negative direction. So they cancel one cancels the other, right? So if both the magnitudes are equal to each other, they will be cancelled out, and ultimately the circuit becomes a pure resistive, like the case what I have discussed in here, right? Now the parallel combination, of course, we prefer to use 1 upon, because we know that the fact that 1 upon ZT, right, 1 upon ZT is equal to 1 upon Z1 plus 1 upon Z2 plus likewise 1 upon Zn. To make it easier, we use 1 upon y's in here. 1 upon Z is defined as y, the admittance. This is impedance. 1 upon impedance is admittance. So admittance, when you redefine all these terms as admittance, you get this equation. So total admittance is equal to the admittances, addition of admittances of all, right? This way the calculations will become easier. However, what you will be actually known initially is the impedance, so you will have to calculate the admittances, individual admittances, and sum of those together. That makes the life easier. In the case of resistances, we did not talk about that. Even in the case of capacitances, we did not talk about that, but now we are talking about it because that makes the life much easier. Okay, right. So phasor diagrams. Now we had those phasors earlier, right? Now we drew the phasors for each components, that is for resistors and capacitors. We actually saw how the voltage and the current interrelates. So now we will take one by one of these and try to combine a circuit together, right? Let's save this, and I'll take okay, I don't think, okay, we can write it in the same thing, right? We don't need any okay, let's take the pen. Right, now here you can see that the current is common to both, so taking a common parameter as reference is easier. So let's take, we can use different colors, right? So we will use okay, we'll use green to okay, now maybe a darker color, right? This one to represent the reference, that is I. Oops, maybe I prefer using we'll use the zonal for that. So this is our circuit, right? That makes my life much easier, right? Okay, so let's use some color, maybe purple, represent the current. Oops, looks like there is something wrong. Yes. Okay, so that's it. Time to time this goes off. I don't know why. Anyway, so let's take I as reference, right? Let's use blue to represent the reference direction, reference, that is I. Now you know voltage and current are in completely different two scales, so you don't have to draw this to a scale. I mean, you can't actually draw the currents and voltage in the same scale, but you need to draw all the voltages into a certain scale and all the currents into a certain scale. If the actual values are known, then you can calculate all angles and things like that using trigonometric trigonometry. You can get all calculate the current values and things like that. Now we'll take voltages one by one. We know that okay, let's go back to that slide where we have the interrelationship between the terms. Okay, there you go. Inductors, resistors, where is that? Okay, for resistor, they are in phase in the same direction. What do we have? We have an inductor. Inductors, we know that the voltage is leading by 90 degrees. So in here, if you draw the voltage VR will be in the on the horizontal axis, because this is VR. The I and R for the resistor are in same phase. For the inductor VL, VL is leading by 90 degrees, so therefore it should be like, oops, why did it take? It should be drawn like this. So this is VL. Now what is V in? You can use the vectors, right? So VR plus VL is our V in. So that's our V in. So V in is equal to VL plus VR, right? Now okay, we can do some mathematical calculations in here. Let's label this as alpha, right? So the magnitude of V in is equal to square root of VR squared plus VL squared, right? And angle alpha is tan inverse VL over VR, right? Now what about VL? VL is I XL and VR is IR. So alpha can be written as tan inverse VL is XL over R, right? I is common, right? So all these are actually derivations. The first point what you need is to draw this. Now you can use another alternative, right? Alternative technique. I'll draw it in here. I is taken as reference, right? So you draw VR all on the same direction. Why do we start with VR? It is because I and V are in the same direction for a resistor, so we go in the same direction. VR, you can start from there, VL. Rather than starting at this point, you can start from the end. So that will be this VL, and two ends will give you V in, right? Again, same alpha would be here, right? Let's save this. Right, so let's check another example, another phasor diagram 2, right? So let's take this out. Again, the current is common to those two, so I'm going to take current as reference. Anyway, we had to take current as reference. There is no other option there, right? Current as reference. Then voltage goes in the same direction, VR. Now the capacitor. For the capacitor, current is leading, voltage is lagging. So voltage is lagging means voltage has to go downwards. So VC goes downwards. And the total of these two is Vn. So this is our V in. Right? That is because V in equals VR plus VC, right, in the complex number domain. So we draw the two phasors, we add the two phasors, and alpha is tan inverse VC over VR. Now the alpha is actually going in the negative direction, and V in is equal to square root of VR squared plus VC squared, right? Or simply you can use the complex numbers, if you know the complex numbers, to add the two values, right? So this is two different cases, like using complex numbers and using the phasor diagrams. The next example, right, when there are three and given a condition as well, XL is larger than XC, right? So let's draw all the options together, or there are two cases actually. Too much, right? Okay, the first case actually is given as XL larger than XC. So XL larger than XC means VL larger than VC. The second case we will draw on the other direction, which is XL less than XC or VL less than VC. So we will draw both, right? So we will take actually this one a little down, right? Okay. Right. Okay, so Okay, so let's take blue as again the reference. Again here the current I is common for all these. So taking I as reference, you can draw the current here, the phasor diagram here, I as reference, then VR goes that way. Let's draw this VR. Then VL goes upwards because VL is leading to the current. Current is this, so VL is leading. So VL goes upwards. I'm going to draw it in different colors now. VL goes upwards and VC actually goes downwards. Now it says VL is larger, so VC goes downwards. VC smaller than in size to the VL, so the result is this. Oops, not that, but this, right? So this is VS, and you can see that it's still in the positive side, alpha, right? So alpha is positive, in the positive direction, right? So this is actually inductive. Then the second case, we will take this relation, that is VL is smaller than VC. Again we will draw it in the using I as reference. We had to use I as reference, no option there. VR will be along the same direction because voltage and the current for the resistors are in the same phase. You might have observed that I was always taking the voltage phasor at the beginning because the current is taken as reference because these are series circuits, and then I drew the phasor of the the voltage phasor of the capacitor or the inductor. Now in this case again the inductor goes in the positive direction because it is leading by 90 degrees, VL. The third parameter is the capacitive reactance. Now it says, or the capacitor voltage, VC is larger. So VC is larger, VC. Now our resultant is, oops, this, right? So VS. Now you can see that the angle is negative, so this is capacitive, right? Phase angle is negative now, right? So nothing to worry, just start from the in phase component and keep on drawing all the parameters, you get the phasor diagram. Now all these examples that we discussed so far, actually the next case is down there, right, are for series circuits. Let's look at okay, let's take a different example. I want to actually take a different example. Let me check if it is there. Into this later. Before that we'll take a different example, just a parallel one, right? Resistor and an inductor parallel, right? So V is actually here. Then you have IR, IL. So so voltage is common in here, voltage is in common, so you have R and XL, right? So here you can see that the voltage is common, so therefore we will have to take the voltage phasor as the reference, taking V as reference, right? So taking V as reference, voltage is drawn. Now the current phasor I R is in phase, because we know that for a resistor voltage and current are in the same phase, right? So I is in that direction. Then I that is IR. IL is which direction? We know that for an inductor, voltage is leading, that means current is lagging, right? So IL. Now from here, if you label this as I, we know that if you apply KCL to this node, right? Applying KCL to this node, I is equal to IR plus IL, right? So you can use that principle in here, and you can mark the resultant current I like this. Again, if you label this as alpha, alpha is equal to tan inverse IL over IR. So this is just simple trigonometry, and I is equal to square root of IL squared plus IR squared. So again trigonometry, right? Pythagoras theorem. So that's for a parallel. You can see that for a parallel circuit, voltage is common to all the elements, so therefore you take the voltage as reference. In the case of a series circuit, the current is common for all the elements, so you take current as reference, and you start drawing the phasor of the resistor, if there is any, first, because the direction of the phasors, voltage and current, are in phase for a resistor. So therefore you start from there. Although it is not absolutely necessary, you generally start from there. Let's take this example, a combination, that is series parallel combination there, right? So let's take that as well. First of all, we will label the parameters. Let's label this as V2 and this as V1 and this as V in. Also the currents, we need the currents as well, so we will mark this as I and I1 and I2. Now in this case, we will have to draw a voltage phasor diagram and a current phasor diagram both. Now we have to start with the far end. Now far end, we have a parallel combination, so you take voltage as reference. So first you taking V2 as reference, you draw the phasor diagram. So V2 is reference. Now at the beginning, because I am not sure whether the other phasors go up or down, I am drawing it in the middle sort of. So this is V2. V2, let's write it neatly. Then we have I2. I2 is actually for the resistor, because so that is in phase. I2 Now keep in mind that the voltages and currents are not into a scale, but voltages should be in a given scale and current should be in a given scale, right? So here I see, right, for a capacitor current is leading, so therefore I1 goes that way, I1 goes that way, and the resultant current I is equal to I1 plus I2. I think it went a little lower, so we'll redraw that. Okay, so this is I. Now we'll have to find V in. For that, this plus this, so we can now take I as reference, right? Second case, now take I as reference. I'm going to draw it in the same diagram, taking I as reference. Shall we move this a little lower, right? I as reference, and it is actually going to be drawn in there, right? So I took I as the reference, V2 would be that way. Now for this, if we take I as reference, V1 will be, okay, for an inductor voltage leads the current by 90 degrees, so the voltage should be going on this direction, assuming that this is 90 degrees. So this is V1. Now V1 plus V2 what so this is our V in, right? Now, okay, unfortunately we in this particular example we don't know any of these values, like the inductor value, capacitive value, and the resistor value, but if we knew those values, we can do some trigonometric calculations in here to find out the voltage, angle values, and so on and so forth, right? So you know the angles, you know the magnitude, so you can do the calculations easily, right? So this actually the angle between the voltage V1 and the current I is a right angle because of this the relationship of an inductor. For an inductor, voltage leads the current by 90 degrees, and the current is I. And the relationship for the voltage V2 and I we have already derived in here. So this is how you do it, right? You know the direction relationship between I and V2. First you had to do that, and then you combine it with this one, right? So now with the last lecture, I have actually uploaded a different quiz as such, but now for this lecture the quiz would be I leave some of the circuits. Now I did this one, but I am not discussing this one, I'm not discussing this one, not even this one, right, and this one. So I leave these few circuits for you to tackle on your own, just to draw the phasor diagrams on your own. I just give you a hint in here. Now in the circuit, okay, I'll switch the screens, that would be easier. In the circuit here we had a parallel circuit at the far end, or we had to tackle the parallel circuit first and then the series part. Now in here you have a series circuit in here, so you'll have to tackle the series circuit first and then you will have to go to the parallel circuit, right? So complete the phasor diagrams for all the other circuits that are in here. and upload that as the second quiz. I'll give you enough time, don't worry about it at all. I'll give you enough time to complete the phasor diagrams, and if you have any issues, always you can reach us via different paths that we have made available, WhatsApp group, and we will be starting group discussions from tomorrow, that this Friday, and with all those multiple methods you can reach us, and you can get the doubts clarified. I think I have discussed all relevant for the first first lecture on AC. So the next lecture would be AC analysis. So we will be starting all the different types of analysis that we were doing with DC circuits with AC circuits. Now in that, I'm not going to actually go into the details of mesh analysis, nodal analysis and things like that, but I will be talking about how we use that knowledge that we gathered in the DC circuits to resolve the AC circuits. So till we meet next time, have a nice time at home, be at home, work hard, and be safe. See you all in the next lecture.